Okay, in a previous video we've talked about linear combinations, and that involves whether you can take a linear combination of certain vectors to produce another vector, right? A linear combination being, so if you have a bunch of vectors, you scale the vectors and add them, that the vectors that you get are called linear combinations. So now we're ready to bring matrices into the picture. And we're going to define a matrix times a vector. So matrix vector equations. So here's the definition. So let's say that you have an m by n matrix and you have a vector x, an element of Rn. Then we define Ax, so this is A times X, so A is a matrix, X is a vector. A times X to be the vector. Okay, so I have to introduce some notation. So A is an m by n matrix. Let's call the columns A1 through AN. So that's our matrix A. And then our vector X has components, say, x1 through xn. Right, so these AIs are vectors. Okay, so when you have this matrix times this vector, what this is defined to be is x1 times the first column, times the first column, that's A1, plus x2 times the second column, plus xn times the nth column. And now notice that the AIs, so A is an m by n matrix, right? So there are m rows and n columns. So I have n column vectors, A1 through AN, but how many components does each of these columns have? They have m, right? There are m rows. So each of these vectors, A1 through AN, these vectors are in Rm. And so therefore, when you take any scalar multiple, right, you're taking x1 of A1, and you're taking x2 of A2 up to xn of AN, and then add them all together. This is a vector, this is an element of Rm. So let's just, in case you don't know, this notation means is an element of. Okay, it's convenient to have this notation instead of having to write is an element of every single time. So it's this simple. Okay. Well, let's look at some examples. And notice, by the way, that this is a linear combination of the columns. A linear combination of the columns of A. So let's look at an example. Let's say I have this matrix 1, 2, -1, 0, -5, 3. That matrix times this vector 3, 4, 7. Well, by definition, so this is our matrix A, this is our vector X. What's A times X? Well, the definition says take x1 of A1, x2 of A2, and x3 of A3 and add them all together, right? So this is going to be 3 times the first column, that's 1, 0. So just to make sure we're really clear, this vector A1 is 1, 0. 2 is 2, 5, and then A3 is negative 1, 3. So 3A1 plus 4 to negative 5 plus 7, negative 1, 3. Now remember, the 3, 4, and 7, those are your x1, x2, and x3. So this is going to give you 3, 0, plus 8, negative 20, plus negative 7, 21. And then this is going to make, so you add the components together, 3 plus 8 minus 7 is 4, and then 0 minus 20 plus 21 is 1. So a times x is 4, 1. Okay, let's do another example. Let's say I had this matrix, the columns are 2, 8, and negative 5, and 3, 0, and 2. And so this matrix times 4, 7. Well, why don't you take a minute and calculate it and see what you get? Pause the video and see what you get. This is an 8. Okay, let's go over the answer. So I'm going to take, 4 of the first column and add 7 of the second column. So this is going to be 4 times 2, 8, negative 5, plus 7, negative 3, 0, 2. And then I'm going to get 8, 32, negative 20, plus negative 21, 0, 14. And then those are going to add to negative 13, 32, negative 6. Yes. Let's do one more example. For V1, V2, and V3 in Rm, write the linear combination ten V1 minus pi V2 plus the square root of 3 V3 as a matrix times a vector. Okay, take a minute and see what you get. All right, let's go over the answer. So we don't actually know what V1, V2, and V3 are, right? But what you're going to do to get the matrix is you're going to make your V1, V2, and your V3 the columns of this matrix. And so this is A, and then you stick in a 10, a negative pi, and the root 3 here. That's your x. That's your vector, right? A times x is going to be 10 times the first column plus negative pi of the second column plus root 3 of the third column. Okay, so those are some basic examples. And, one of the nice things about this is that if you have a linear equation, so let's say that you had 3, 5, 6, 2, 0, 1, and then 3 unknown constants, right? This is going to equal x1 times 3, 2, plus x2 times 5, 0, plus x3 times 6, 1. But what's that going to be when you write it out, right? When you have x1, so this is a scalar, times this vector, what you do is you multiply each of those components of the vector by the scalar. So this is going to be 3 times x1, and then 2 times x1. And then similarly for this guy, what's that going to be? That's going to be 5 times x2, and then 0x2. Well, 0x2 is just 0. And then the last one's going to be 6 times x3, and then x3. And now you can add these and get the vector 3x1 plus 5x2 plus 6x3 to x1 plus 0 plus x3. Right? And now it's looking like a system of equations. So for example, if I had the system of equations 3x1 plus 5x2, let's use the example above, plus 6x3 equals 10, 2x1 plus x3 equals negative 5, right? This system of equations can be written as a matrix times a vector equation. The book by Lay calls it a matrix equation, but I usually call it a matrix vector equation. And how do we do that? Well, we've explained how the left-hand side, right, can be written as a matrix times a vector. It's gonna be this. Right, it's written as, so I take the coefficients and then multiply it by this vector, x1, x2, x3. Right, so we've gathered all the variables. There's 3 variables, but we've gathered that into a single vector x. This vector x contains all your variables. And then this matrix A contains all your coefficients. And then it's this matrix times this vector is, so this thing on the left, okay, this A times X is the thing on the left here, and then written as a vector, and then the thing on the right written as a vector is 10, negative 5. Right? And often this is called B. And so that shows you how to represent the system of equations as one equation. And notice that here in the original system, right, you have 2 equations. But here, and in any system of linear equations will have a bunch of equations, but the point is that when you have this matrix times a vector equals another vector, you have only one equation to work with. So that's good. So it's just nice to have this compact way of writing out a system of equations. Okay, so that's it for this video. I'm following section 1.4 of Lay's book, Linear Algebra, the 3rd edition, and then we'll continue and do some more examples later. Thanks.